Now let's find the required maximum voltage or voltage rating of the employed switches, as well as the required voltage rating for the employed capacitor. So for the switches S1 and S2, obviously when one switch is on, the other is off. So say if S2 is on, this voltage will be 0 or connected to 0. And so the maximum voltage across S1 will be essentially the input voltage. And similarly for S2, so the maximum voltage for switch 1 or switch 2 is going to be the input voltage. And so when we order the switches or the transistors for implementing a series resonant pulse inverter for a wireless power transfer system, we should make sure that their maximum voltage, the maximum voltage the transistors can handle, should be larger than the input voltage. As for the capacitor, well, we already found an expression for the current in the series resonant circuit, right? It's given by 2VI cosine epsilon over pi times R sine omega t minus epsilon. And so let's call essentially let's call the amplitude of the current as I capital M sine omega t minus epsilon. And so the voltage across the capacitor will be the current multiplied by 1 over omega c, the reactance, right? Or the amplitude of the voltage will be Im over omega c. And we know that the maximum value for Im, the amplitude of the resonant circuit current, will happen when epsilon is equal to 0 at resonance, when the switching frequency of the half bridge matches the series resonant frequency of the RLC circuit. And so we can say that the current at resonance, or let me VC max, will happen at resonance and will be equal to 2VI pi times R, and then we have omega c, omega naught c, because we are operating omega is equal to omega naught. We said before that the loaded quality of the RLC circuit is equal to 1 over omega c R. And so we can replace this by QL times 2VI divided by pi. And we know that 2VI over pi is basically the amplitude of the fundamental component of the voltage generated by the half bridge. We said that the half bridge produces a square voltage, and so it consists of harmonics and a fundamental component, a DC component, fundamental and higher order harmonics, and the amplitude of the fundamental component is given by 2VI divided by pi. And so the point here is the maximum voltage that the capacitor sees is QL, the quality, the loaded quality of the RLC circuit, is QL times the fundamental component of the voltage applied by the resonance circuit. And we know that QL typically, we select QL to be larger than 2.5. So that the bandpass filter has a tight bandwidth and it can select only the fundamental component and reject the third order harmonic and higher order harmonics. And so this means that the maximum voltage across the capacitor is typically larger than the DC input voltage. And the higher the quality, as we apply higher and higher quality, for the RLC circuit, the higher or the larger the voltage that's applied across the capacitor, and the maximum voltage rating of the capacitor increases. Now, to be able to select or find the required equivalent on resistance of the applied switches, we need to calculate the efficiency of the series resonant pulse inverter. And to find the efficiency, we'll need to find an expression for the output power as well as the input power, because efficiency is the ratio between the output power and input power. So let's find first what is the output voltage, and from the output voltage we'll be able to calculate the output power. So the voltage across the load will be the current multiplied by the load resistance Ri, which is equal to Im times Ri. Again, Im, we said, is the amplitude of the current I, which is equal to 2Vi divided by pi r cosine psi multiplied by Ri times sine omega t minus psi. Now, the maximum value for the voltage across the load resistor, the maximum amplitude, is going to happen again when cosine psi is equal to 1, so at resonance. Okay, and so at resonance, the amplitude of the voltage across the load resistor will be equal to 2Vi divided by pi r, which is equal to the amplitude of the fundamental component in the applied square voltage Vt. And so when I mentioned that the maximum voltage that the capacitor has to block is actually going to be the loaded quality times the maximum amplitude of the voltage across the load resistor at resonance. And so essentially is going to be larger than the voltage that's delivered to the AC load, given that quality is typically larger than 2.5. Now, after we found an expression for the output voltage, we can find the power delivered to the load resistor as the amplitude of the current, Im square, but we'll divide it by 2 since it's sinusoidal current that's going into the load resistor. Its RMS value is 1 over square root 2, and then we square that, so we have Im square divided by 2 times Ri. And of course, you can replace Im by its value from this expression. And so we get 2Vi square times cosine square psi divided by pi square r square, and all that multiplied by Ri. So that's the expression for the output power. Now we need to find the input power. And the input power is the power that's taken from the input source. And to find this power, we need to find the current that's taken from the input, which is basically the current that's going in S1. And so the current that's going in S1, or the input current basically, as we said before, S1 is turned on for 50% of the cycle time. And so the current that flows, or the resonant tank current, is going to flow in S1 during the first half cycle, or while omega t is between 0 and pi. And otherwise, the switch will be open, and so the current will be 0. And so the current is equal to the tank current in the first half, which is Im sine omega t minus epsilon, and otherwise it's 0. Now, to find the input power, we need to calculate the average value of the input current, because the average value of the input power is equal to the input DC voltage Vi times the average value of the input current. And the average value for the input current will be essentially 1 over 2 pi, the cycle time in radians, 0 to 2 pi, the input current II, as a function of omega t, and we integrate with respect to omega t. So we know that the current is going to be 0, the input current is 0 in the second half cycle, and so this integration boils down to 1 over 2 pi, 0 to pi, this expression Im sine omega t minus epsilon d omega t. And so let's perform this integration. When we can take Im outside, divided by 2 pi, and then the integration of sine is going to be minus cosine, and the bounds of the integration will be from 0 to pi, but since we have a minus sign, we can say it's going to be from pi to 0. So Im divided by 2 pi, replacing omega t by 0, we get cosine minus epsilon, which is cosine epsilon, minus, we replace omega t by pi, so we have pi minus epsilon. And we know that cosine pi minus epsilon is basically equal to minus cosine epsilon. And so we get Im divided by pi times cosine epsilon. Okay, and that's the average value of the input current. Now we can find the input power Pi as the input voltage, DC input voltage Vi, times the average value of the input current, which is going to be equal to Vi times Im over pi cosine epsilon. And simplifying this expression, we can get, if we replace Im by its value as 2Vi divided by pi r cosine epsilon, we'll get that the input power is going to be 2Vi square Ri we'll get the input power Pi is equal to Vi times the average value of II. And so the input power is going to be 2 VI square cosine square epsilon divided by pi square